Today I'll be showing you how to do partial derivatives. So say you have a multivariable function like f of x and y equals x squared y plus 3y. A partial derivative is when you take the derivative of a multivariable function with respect to one of the variables, meaning you treat any other variable as a constant. So for example, we could take the partial derivative of this function with respect to x, and you could write it like this. But a much easier way to write it is just f subscript x. So that means the partial derivative with respect to x. So remember, we need to differentiate the whole thing with respect to x and treat y as a constant. So for the first term, we can multiply everything by 2 because it's x squared. Then we can write the y because it's a constant, and then x to the power of 1. And then next, for the 3y, because y is a constant, that would just differentiate to 0, so we can just leave it out. So the partial derivative with respect to x is just 2yx, or 2xy. And you can also take the partial derivative with respect to y, and that follows the same process. The only difference is you differentiate with respect to y, which means you would treat x as a constant. So to do that, for the first x squared plus y term, it would just become x squared, because the y is to the power of 1, and x squared is a constant. And then next, the 3y would just become 3. So that's our partial derivative with respect to y. Alright, now let's try this one with 3 variables. So this time it's f of x, y, and z. So because it has 3 variables, it's going to have a partial derivative with respect to x, y, and z as well. To get f subscript x, we need to differentiate with respect to x and treat y and z as constants. So for the first term, using the power rule, we can take the power of 3 on the x and bring it out the front to multiply everything by 3. And then we can do x squared, and we can put in the y squared because it's a constant. Next, yz cubed. Y and z are both constants, so it just becomes 0, so we can leave it out. And the derivative of e to the power of x is just e to the power of x. Next, let's get the partial derivative with respect to y. So we're just going to differentiate with respect to y and treat x and z as constants this time. So the y squared in the first term is going to become 2y, and then because x is a constant, we can just write in x cubed. Then for the next term, because the y is to the power of 1, it's going to disappear, and we can just write z cubed. And finally, because we're treating x as a constant, e to the power of x is also going to be a constant, so it's just going to differentiate to 0, so we can just leave it out. And f subscript z is going to follow exactly the same process. So x cubed y squared is just going to differentiate to 0, because it doesn't have a z in it. For yz cubed, the z cubed is going to become 3z squared, and then we can just write in the y, because it's a constant once again. And the e to the power of x just becomes 0, because it doesn't have a z in it either. So those are our 3 partial derivatives. And you can also do higher order partial derivatives, like how you might take the second or third derivative when differentiating single variable functions. So say we have f of x and y equals x squared y cubed plus e to the power of xy. Well, there's actually going to be 4 different possible second order partial derivatives because we have 2 variables. So that means you can do the first partial derivative with respect to x, and then the second with respect to x again. Or you can do the first with respect to x, and the second with respect to y. We can do the first with respect to y, and the second with respect to x. Or you can do the first with respect to y, and the second with respect to y as well. So let's find all the second order partial derivatives. But first I'm going to find f subscript x and f subscript y, just so we don't have to repeat ourselves later. So f subscript x is going to be, well, for the first term, the x squared becomes 2x, and then we write the y cubed, and e to the power of xy. To differentiate an e term, you multiply it by the derivative of the power, So it's going to be y times e to the power of xy. And f subscript y, for the first term, the y cubed is going to become 3y squared, and then we can just write in the x squared. And the e to the power of xy is going to differentiate to x e to the power of xy. Alright, now let's see if we can find all the second order partial derivatives. So let's start with f subscript xx. So first we need to differentiate with respect to x, which we've already done. So that's just 2xy cubed plus y e to the power of xy. And now, to find f subscript xx, we need to differentiate with respect to x again. So to do that, for the first term, because the x is to the power of 1, it's just going to be 2y cubed. And for the second term, y times e to the power of xy, we differentiate the e term once again by just multiplying by the derivative of the exponent, which is y. So it's going to be y squared e to the power of xy. So that's our answer. How about f subscript xy? Well, to get that, once again, first we need to find the partial derivative with respect to x, which we already found out was 2xy cubed plus y e to the power of xy. And now we need to differentiate again, but this time with respect to y. So doing that for the first term, using the power rule, we multiply everything by the 3, so it becomes 6x, and the y cubed becomes y squared. And for the second term, because we're differentiating with respect to y, and we have y times e to the power of xy, we're actually going to need to use a product rule, because this is a function of y times a function of y. So differentiating with respect to y using the product rule, and I'm not going to go over the product rule, because I'm just going to assume you already know how to do it if you're learning partial derivatives. But you get e to the power of xy plus x, y, e to the power of xy. So that's f subscript xy. Alright, now let's do f subscript yx. So this time we need to start by differentiating with respect to y, which we've already done. And it's just 3y squared x squared plus x times e to the power of xy. But now we need to differentiate again, this time with respect to x. So doing that, you get 6x y squared, and once again, we're going to need to use a product rule for x times e to the power of xy, because it's two functions of x being multiplied together. So that just ends up being e to the power of xy plus xy e to the power of xy. And you might notice that this is exactly the same as f subscript xy. And that's because of something called Clairaut's theorem. And I'm not going to go into too much detail on that, but basically all you need to know is that when you're just starting to learn partial derivatives, basically for every function that you're going to be working with, f subscript xy is going to equal f subscript yx. But anyway, let's figure out f subscript yy. So once again, we need to start with f subscript y, and then we need to differentiate again with respect to y. So doing that, the 3y squared x squared is just going to become 6x squared y, and then the x times e to the power of xy is going to become x squared times e to the power of xy, because we multiply by the derivative of the exponent of the e term. So those are the four second order partial derivatives. So when taking higher order partial derivatives of a multivariable function, you can differentiate with respect to any variable at each step and in any order. So for example, a function f of x, y, and z would have 9 second-order derivatives. xx, xy, xz, yx, yy, and yz, or zx, zy, and zz. Alright, now that we've gone over the basics of partial derivatives, let's try some examples. So here we have f of x and y equals y times sine e to the power of 3x plus x times y. So have a go at finding f subscript x and also f subscript yy. Alright, first off, to get f subscript x, we just need to differentiate with respect to x and treat y as a constant. So for the first term, we need to multiply by the derivative of e to the power of 3x, because that's just how you get the derivative of trig functions. And also the derivative of sine is cosine. So it's going to end up being 3 times e to the power of 3x, y, cosine e to the power of 3x. And then for the second term, x times y, because x is to the power of 1, it's going to disappear, and it's just going to be y. So that's the partial derivative with respect to x. Now, for f subscript yy, we need to start by finding the partial derivative with respect to y. So for the first term, sine e to the power of 3x is basically just going to be treated as a constant because there is no y in it. And because the y is to the power of 1, it's just going to disappear. So the first term becomes sine e to the power of 3x. And the second term differentiates to x. And now, we need to differentiate with respect to y again. And because sine of e to the power of 3x doesn't have a y in it, it just differentiates to 0, and x also differentiates to 0. So that means that the answer to f subscript yy is just 0. Alright, and finally, for this function of x, y, and z, see if you can find f subscript x, y, z. So that's going to be a third order partial derivative. So to find f subscript x, y, z, first we're going to need to differentiate with respect to x and treat y and z as constants. So for the first term, the x squared is going to become 2x, and then we can just write in the y cubed z. For the next term, differentiating e to the power of x, y, z with respect to x gives yz e to the power of x, y, z. And the derivative of the natural log of x is just 1 over x. Okay, so now that we have that, we need to differentiate again, but this time with respect to y. So f subscript xy, we're going to multiply by the power of 3 on the y. So the 2 is going to become a 6, and the y cubed is going to become a y squared. Next, yz times e to the power of xyz is going to need the product rule, because yz can be treated as a function, and e to the power of xyz can be treated as a function as well. So if you differentiate that with respect to y using the product rule, it's going to be z e to the power of xyz plus yz times xz e to the power of xyz. And next, the 1 over x is just going to become 0 because it doesn't have a y in it, so we can treat it as a constant. And finally, we need to find f subscript xyz by differentiating again, and this time with respect to z. So for the first term, the z's just going to disappear because it's to the power of 1. So it's going to become 6xy squared. Our next term is going to require a product rule again because it's z times e to the power of xyz, and we're differentiating with respect to z. So that just becomes e to the power of xyz plus xyz e to the power of xyz. And then for our final term, first let's just quickly multiply out the brackets to make it simpler to differentiate. So it's going to be x, y, z squared times e to the power of x, y, z. And because that can be considered as a function of z times a function of z, we're going to need to use the product rule again. And doing that just gives you x, y, z squared times x, y, e to the power of x, y, z, plus 2 x, y, z times e to the power of x, y, z. And now let's just quickly simplify that. So if we multiply out the brackets, we get 6xy squared plus e to the power of xyz plus xyz e to the power of xyz plus x squared y squared z squared e to the power of xyz plus 2xyz e to the power of xyz. And then you can get our final answer by simplifying even further by factoring. And you get 6xy squared plus e to the power of xyz times x squared y squared z squared plus. And because we can actually collect like terms and make this 3xyz e to the power of xyz, we can do plus 3xyz and then also plus 1 for the e to the power of xyz term that's by itself. And that's the final answer. So that's how you do partial derivatives. Thanks for watching.